So where's those symbols at? Inside course content, handout and reference material, and then electrical symbols. So here's a photodiode, right? Y'all see a photoresistor? I'll see if I can find a chart that's got the symbols on some of those other devices. So like I said, I'll see. The only one I see here is a photodiode. That's the only symbol I see on that symbol chart. I'll see if I can find another one. I'll put it up there for you. Here is, of course, test. Of course, y'all can't see. Then under course test, you should have test reviews. And I got to make this visible. And review for test 1. So if y'all can see this and open it up, y'all need to tell me if y'all got any questions, that's anything on this review that we need to go over. This is not the right one, guys. I'll have to put it, we got 2 more things on here. One of them is you're going to have to know the rules for relay logic, because it looks like some of y'all will have that. And another thing that's going to be on here is symbols. You'll need to know the electrical symbols, because some of y'all was having problems on that. Transfer function, are we okay there? What's the transfer function? You might know what a transfer function is. I'm waiting.
We don't know which is.
So y'all even actually did some calculations of that. Maybe you need to go back to that. So a transfer function is, so what does a sensor do? No, all sensors do the same thing. All sensors do have exactly this. Now, what they sense might be something different, but all sensors do the same thing. All the sensors on your body do the same thing. What does your senses do?
A physical stimulation to a visual or something like that. I forget the exact definition.
Yeah, so it's a device that takes a physical stimulus and converts it into an electrical equivalent. That's what a sensor does. Okay. So what we're going to do is we're going to get something out of the sensor, and we're going to put something in. And this is what we call the transfer function. This allows us to tell us what volts we get out when we put 90 degrees in. So if I knew I had this, temperature sensor down here, let's put it the other way, because we want our voltage to go up with temperature. So what if I measure 10 volts and this equal to 100 degrees? So, well, what are we getting out? What is this? This is what we're measuring. This is what we're putting in. So what we're going to do is we're going to get degrees out. We're putting volts in. So my transfer function would be equal to 100 divided by 10. So what would this be? 10 volts. Volts is on the top. Volts, what's on the bottom? Per degree. So what if I did 25 volts? What if I measured 25 volts?
Are we talking for the same degree too?
What's that? Huh?
Are we talking for the same degree, like 100 degree?
I'm sorry. Let's say I measured 2.5 volts. I went too high. What would be the temperature?
See, I'm confused because you wrote 100 degrees and then you wrote 100 volts. You see, you got the degree sign about 100 and then you wrote 25 volts. Okay.
I'm sorry. Transfer function. What are we getting out? This is wrong, guys. What are we getting out? We're getting volts out. We're putting degrees in. So my sensor is seeing. Okay. Well, that was. So Rich made a mistake. I'll write that down. So what are we putting in? So my sensor is putting. What are we putting into my sensor? We're putting what in? No, we're putting. My sensor is sensing what? What's putting? Sensing what? It's sensing degrees. And what is our meter measuring? What are we getting out? We're getting volts, right? You understand? So my transfer function, I'm sorry about that, guys, would be 10 divided by 100. And this is volts. This is degrees. So what my transfer function would be?
1 to 10.
So it's going to be what?
1 minute. Yeah. 1. Yeah, would it be 1 minute?
What's that? I can't take 10 and divide it. It's going to be, well, I know this will cancel and this will cancel. So somebody said 1/10, but we don't deal with 1/10. What would 1/10 be? Somebody said it.
100 millivolts.
Okay, so this would be 100 millivolts per every degree, right? Everybody okay? So we're getting volts out. We're putting degrees in. So, okay, I want to know what temperature, if I measure 2.5 volts on my meter, what temperature would that be? So we're solving for degrees. So my transfer function is equal to volts over degrees.
25 degrees? 25 degrees.
Yeah.
25 degrees.
Good. So we would just transpose the formula, right? You understand? It would solve for D. So D would be equal to what? V over the transfer function. Everybody okay? So what did y'all get? 25 degrees. So out over in. So what you're going to have, so all transfer function is what you're putting in. So this is going to be what you're sensing, right? You understand? On what you're getting out. And the two things that we can get out would be a watt, we can get a volts, which is by far the most popular. Or what would be the other one? Current. This is an example of a voltage sensor. So what is the transfer function? It's the ratio between what you're putting in, what your sensing element is sensing, and what you're getting out. Everybody okay? Okay, guys, sound like y'all need a break. Y'all go ahead and take another 15-minute break, and we'll wrap this up, okay?
Okay. All right. Yeah, would you turn your mic on and off every time you say something? You'll click it on, you say, okay, you'll click it back on. Yeah, okay.
Okay, good. So, I finally got the right test review to upload. So the revised rules for relay logic, those are up there in the handout section. The electrical ladder diagram symbols, which some of y'all had problems with. So what we're doing is looking at these terms here, guys. Y'all need to tell me if there's anything y'all need to go over.
When exactly is it going to have test in?
We'll have it at this Wednesday. This Wednesday. It was actually due today, but we've had so much going on, and we've covered basically everything that we've got through. In fact, light sensors are not even on here, I don't think. So we're actually a little ahead on our lectures, which I thought we'd be because we don't have any labs going on. And then, so y'all need to look this over and see if anything y'all want to go back over.
What will be the format of the test? Will it be multiple?
It'll be multiple choice, true, false, yeah. So there won't be a written section on this. None of the tests in this class have a written section on them. They're all multiple choice.
Yeah, well, I don't know if that's a good thing or bad thing coming from Rich. Oh, my bad. Can't hear it, Rich.
Yeah, I recorded it too. And I will bring it back up. I might even put that on Facebook.
That was complete bad. That question. And that thing there, I'm just letting you know.
So y'all look this over. Yeah, but y'all need to look this over and see if there's anything on here that we need to go back over.
What time is the moment that you're going to be 9 o'clock today? So you give us the whole day schedule.
No, we'll have a lecture before we got two options. We could take the test first, and it will be timed, or we can be in lecture, but then we'll be in lecture after that, or we can take the lecture first, and then if you get through the test early, you'll be through. It's up to y'all. So y'all want to take the test at the start of class or at the end of class?
No, at the end.
At the end? Okay. So what we'll do, we'll talk about speed sensors before the test, but the speed sensors will not be on the test. So what you see here, this is what's going to be on the test. So you need to look, y'all listen up, you need to look at the discussion section on the proximity sensors, which will be, and look at these things to get these definitions right here. I think they're also in the sensor section of the dictionary that I provided. But these are in the handouts that the actual first part of the
So the more the leakage current goes up, the less the less the leakage current goes down.
It's relative to what you're talking about. This leakage current is relative to all solid state sensors. So when we come up here under labs, and this is where I showed y'all, so where's labs at? Laboratory. So what we've been working on primarily right now is, and y'all have access to this, so proximity sensors, and this is where a lot of these terms are going to be at. So when we talk about leakage current, that will be almost any solid state device, right? Oh, I'm sorry, wrong thing. So this is in handouts. Then this is proximity sensors, which is what we're in right now. And then when you look into the discussion, something that loads up. So this is a good question, but so this is technically, besides for my PowerPoint, this is technically your textbook. That talks about NPN and PNP. We looked at that. Then in here somewhere, load current. So this is the definition we're looking for, right? Operating current, holding current. So this is where we're looking at those. Was leakage current on there? On the review?
So, state what you were telling us the last time about the white and the black and the brown.
These are the standard color codes for solid state sensors and reed switches. We talk about solid state, but a reed switch is not technically a solid state sensor, but it falls into that proximity sensor category. So on these color codes, we got 3 color codes that we look at, right? The industry standard now, I'm not saying you might not run into any of, because some manufacturers might not use the industry standard. So what are the industry standards for color, for DC sensors? For the colors? So we have brown. We have blue. We have black. And we have white. So what's the brown? Yeah, this runs toward L1. It might not be connected to L1, but it runs toward L1, right? You understand that? Now the blue is connected to, this guy right here is connected to the minus. So what I'm saying is I come over here and I got this sensor, and it's a 3-wire sensor. Over here I might have this, right? You understand? So over here I might have a contact. So we can hook this in a circuit, and all control devices go between L1 and L2. So I might have this one. Then over here I might have my solid state sensor. Then my load over here. And then this guy is going to go over here and connect. This guy that points toward L1, this right here is going to be brown. But it doesn't have to be connected to L1. This guy is going to be blue, and it's going to connect to the minus. This guy is going to point toward the plus, right? You understand what I'm saying? Yes or no? And then what is this color right here going to be? Yeah. So this is actually what runs the load. And of course, this guy here is going to be for a normally open switch. Now, if I come over here and I redraw this, and then I have a what? The brown points toward L1. The blue connects to L2, or connects to the minus, I should be saying that. And then we might have a black, and then we might have a white. So when we get into this, what we have is we have a 2-position. We have a single pole, single throw double throw switch. The normally closed would be white, so this is the normally closed. And then the normally open would be black. So these are the standard color codes that we would run into. Now, even in AC, if this is an AC sensor, we still want to point the brown toward L1, and we still want to connect the blue to L2, right? You understand that? Just to keep the code. Now, 2-wire sensor, we've only got 2 wires. What's their color?
Brown and black.
Close.
Brown and blue.
Yeah, brown and blue. So this is the big difference here, because the blue, on a 2-wire sensor, the blue connects to the load. So on a 3-wire sensor, there's nothing between the blue and the minus, right? On a 2-wire sensor, blue has got to point toward L2, but now it's going to go through the load. So that's the big difference between a 2-wire sensor and a 3-wire sensor or a 4-wire sensor. On a 3-wire sensor, blue connects to the minus. On a 4-wire sensor, blue connects to the minus. On a 2-wire sensor, blue connects to the load. So that's a big difference, guys. So that's a really good question there. So, and why do they do that? I don't know. That's just the way it is. So, like Capri would think, I would think it would be black, but blue has got to point toward L2. Blue is one of your power leads. So here, these guys are powering through the load. So these guys are going to drop a voltage from what? What I say, between a range of 4 and 6 volts. Because they got to create power to run the electronics in there. So good question, guys. Any more? I'm looking for the review. I guess that's it right there. Yeah. The load current, operating current, leakage current, that should be in the handouts. It's either going to be in the actual discussion section or in the lab itself. So some of these you'll have to look through all three of the labs that deal with proximity sensors. And every one of them's got a real discussion section in it. And this is primarily going to be your textbook for the class. So just like any other class, when you give out a test, and if you got a textbook, if you don't know it, then you're going to look it up in the textbook, and here we also too. But you also might see if it's inside the dictionary. Oh, this is lab. So inside the handout section.
Have you officially posted the review?
Yeah, it should be.
What's it saying that it's locked?
Huh?
It's saying that it's locked.
Just wait a second. Let me make sure. So here's course test. Here's course review. Now test is locked, but the review is there. So yeah, test 1 is locked. So you'll see test 1, test 2, and test 3, but then you'll see another folder that says test reviews. So those will lock until I provide the password. I'll probably provide the password through a message to y'all, because y'all be on Blackboard anyway. And that way it should pop up. And like I said, this is the first time we've actually done this, so we'll just have to wait and see what type of problems we come up with, and I'm sure we'll come up with some. But this is also a really good resource right here. This is something that I'm putting together. So there's a section here on symbols. And holding, these other should be in there too. So this should be a good resource for some of the definitions that I ask you for too. Page number 62. So there's load current. I don't see leakage current in there, guys, so I got to put that one in there. Let me make a note on that. But this will be a good reference too, and if there's any... Leakage current is how much current that gets through a solid state sensor. A solid state sensor is not the contact of a solid state sensor is not a contact, it's a simulated contact. And all solid state sensors, there's a path for current to get through. So all solid state sensors will have a current going through, even though that black wire is 0. When you measure it, it's not going to measure 0, by the way. It's going to measure a current. And that's some of the things that we'll show y'all I'll have to show y'all on the lab. But I'm going to have to figure out how to do that. The only thing right now I know, I don't know who that is. The only thing I know right now I can do for a lab is for me to go into the campus, hook up a camera, and do the labs, and let y'all record the readings as we go through it. That's the only way I can fix it. I know that's not the optimum way, but that might be the only way we're going to have to do that this semester, is I'll have to do the labs. And if I do them, they'll be hooked up right? So I'll figure out who's designed, yeah. So we'll do that. So I know there's one, and if y'all see any terms that we use about sensors that is not inside this dictionary, just send me a text and I'll get them in there, because this is a really good resource. So right now I've already found one. I don't have leakage current in here. I have load current, and see, I don't have holding current either, so I'm gonna have to go back and put some of those in the dictionary. So right now, what y'all need to do is make sure y'all read the discussion section on the labs. Okay, any more questions?
Hold on.
Let me try to bring the review back up there. Current loop is a method that we use to transmit signals, and you'll probably run into these in industry. They're still very popular. We looked at this way back in, I think, one of our first lectures when we was getting. So sending a voltage is pretty easy, but what we do on a current is we come up here. Let me bring up the PowerPoint. So what we do on a current loop is we have the power supplies down here, and then it goes through the sensor, and then it comes back and goes through the receiver, and then goes back to the power supply. Now what they do on a current loop, and anybody remember the values? No, I'm sorry. 4 milliamps to 20 milliamps. So what happens is this guy right here, the minimum current, so this right here would represent a 0. This right here would represent the maximum value. So if I was using digital, it would switch from 4 milliamps to 20 milliamps. What advantage does using a current have over a voltage? So what we do on something that uses volts is these are going to be high impedance or high resistance circuits. So what happens is when an EMI, electromagnetic interference, comes through these things, it's going to induce a voltage. Now, which means if we're going to use voltage, we're going to have to do something to get rid of this EMI. It's almost impossible for a magnetic field to move through a low impedance circuit, which is what a current loop is, and produce a voltage, because it can produce a voltage, but it can't produce a current. So this would be like static electricity. Static electricity is 20, 30, 40,000 volts, right? You understand? Why don't static electricity kill you? So we pick up static electricity all the time. We pick up electromagnetic interference. Thank goodness. That's what makes your touch screen on your computer work. So let me bring my camera back up. Hopefully I still got it on. And what I'm going to do is I'm going to get one of my scope leads, my green lead. Oops, sorry. So I'm a high impedance source, right? My body resistance is really high. I don't see my trace, guys. So all I'm going to do is I'm going to touch the scope probe. So all I'm doing is I'm taking the tip of the scope probe and I'm touching it with my finger. So where's this coming from? Well, it's coming from Alabama Power, 360. So these are high impedance circuits. I'm a high impedance circuit, which is what these voltage circuits do. So it means we're constantly coming up here. Now, why isn't this killing me? Because I'm high impedance. I'm not trying to produce a current. I'm trying to produce a voltage into 10 megohms, which is what this thing is. Well, that means if I have a low impedance circuit, like a current loop, it's almost impossible. In fact, it's just about impossible for electromagnetic interference to change a current. It can change a voltage, but it can't change a current. So this is why current loops are very, very popular in industry, because they're almost impervious to EMI. But what's the disadvantage of that? So this is my power source. And what is it? Current loop. So it loops like this. What is it? 4 to 20 milliamps. And it's almost impervious to EMI. But the problem is even when it's sitting here not doing anything, it's still conducting 4 milliamps. So this guy consumes a lot of power. I got 1,000 sensors out there. Every one of them's running a current loop. Each of them's pulling 4 milliamps apiece, right? All the time, up to 20 milliamps if they're generating an output. But what's nice about a current loop is that it's almost immune to electromagnetic interference. I'm not going to say something, if a nuclear bomb went off, these guys would have problems with that. Or if lightning struck it, it would have problems with that. But, regular EMI that we get inside industry. So what we got to do on voltage is we got to shield the cables. We use shielded wire. We use twisted pair wire. We use all different types of things to keep EMI out. So the biggest problem we have with using voltage is it's susceptible to EMI if we don't take precautions. Current loop, I can just run wire. So it's a lot cheaper. I've seen current loop run, good gracious, thousands of feet with just regular old wire, not shielded wire or anything. So, so 4 to 20 milliamps. This is standard current loop right here. So 4 is the what? This represents a value of 0, and then 20 milliamps would be what? Would be max. Are y'all still out there? So that's a good question. Any more?
Yes. Where will we find the resistor color code sheet? Is it listed on the reference as well?
No. The resistor color code?
Yes, sir.
No. That'd be like saying, where do I find the keys to my car? Or where do I get, that's something y'all should know, right? So Ohm's Law you should know. The resistor color code you should know. Yeah, I know, but that means why I keep putting it in test. Why? Because I want you to keep going back and doing what, Capri? I want you to keep going back and reviewing it. And hopefully by the time you graduate, you'll know the resistor color code, because I'm going to make y'all keep going back and doing what? Reviewing it. So
do you have it posted for review too as well?
No, y'all can look that up on the internet. Just look up resistor color code, and on the internet you can get that. Ohm's Law, y'all should know Ohm's Law, Kirchhoff's Law, Watt's Law. That should be something that y'all know by now. The internet is really, really neat, right? So if y'all don't know the resistor color code, if you need to restudy that, you need to go back. And that's not only the color code for resistors. That's the standard color code for inductors. That's the standard color code for capacitors. I've seen it used on diodes before. Use that same color code. So that's a standard code. Y'all learned it for resistors, but they also apply to capacitors and also inductors. So that's a good question.
What about the Wheatstone Bridge?
Wheatstone Bridge, we talked about that, right? Huh?
Yeah, I'm just going to do like a quick review of that too. But that should be it after this.
So Wheatstone Bridge, a lot of times they come in and they draw it like this. And these are resistors, guys. They're not inductors. And what we do is we're going to take our voltage right here between this. I like drawing it like this because it's easier for me to see. And so this is exactly the same circuit drawn a little different. And what this down here will be our common. Up here I'm going to put this up to plus 10. And I'm going to put a voltmeter right here. So this is where this would be the output of our circuit. And what I'm going to do down here is I'm going to make these two rheostats. So I'm going to set this to 10K. 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 What would my voltmeter measure? So this is a series circuit. All the voltage has to be dropped within a series circuit. Resistors of the same size drop the same voltage. So that means this guy right here has got to drop 5 volts. This guy here's got to drop 5 volts. This guy over here's got to drop 5 volts. This over here's got to drop 5 volts. So we're referencing to here. So that means I have plus 5 volts right there. I have plus 5 volts right there. So what's my meter going to measure? It's measuring a difference in potential. So if I was to come over here, and you're right, if I was to do this, it's going to measure how many volts? Plus 5. What's the difference between plus 5 and plus 5? What's the difference between plus 5, plus 5? 0. So my meter would measure 0 volts. When we do this, this would be balanced. I could come over here and change this to my pen's got all tangled up, guys. I don't have enough room. I could change this to I could change this to 20K. I could change this to 20K. And what would my meter measure? I'm waiting. It's a series circuit. The sums of the voltage drops in a series circuit have to equal to the applied voltage. I'm moving my hands around, by the way. Resistors of the same value in a series circuit drops the same voltage. So I've got 10 volts up there. I have a 20K and I have a 20K. They're the same size. They have to drop the same voltage. And what? And it's got to drop 10 volts. So if they got to drop the same voltage and it's got to drop 10 volts, they're the same size, then what happens? Then this is still going to be what? This is still going to drop 5 volts. This is still going to drop 5 volts. It's still going to put plus 5 volts over there, plus 5 volts over there, and it's going to measure 0. Because what would happen if I was to come over here and it's just a series parallel circuit. It's where we're making our measurement is probably what's throwing you off. I mean, it's where we're making our measurement. We're making our voltage measurement. We're not making it relative to common. We're making it relative to this guy right here. So if this is R1 and this is R2 and this is R3 and this is R4, what we're looking at is the voltage drop across R2 and the voltage drop across R4 because that's our circuit common, right? You understand that? So if I was going to measure, I would measure between my common right there. But if I was to make this a 1K, and I was to make this a 5K, and I make this a 10K, and I make this a 50K, what would my meter measure? This is going to drop. This is going to drop 1/6 of the voltage. This is going to drop, I'm sorry, this right here is going to drop, let's see, 5/6 of the voltage. This is going to drop 5/6 of the voltage. So what's 5/6 of 10? We're using a famous formula that they should have taught y'all in DC. The problem is how did y'all learn DC? Normally you calculated RT, so I'd say the voltage drop over here would be equal to 10 divided by 10 volts divided by 6K, right? And what did y'all get for I? So IT would be equal to what? 10 divided by 6. Everybody okay there? Of course, this is...
Let me go find my... Hold on, let me get my calculator. Because you got me over here rethinking life for a minute. Hold on.
Are you? So back in DC, you learned that this right here, what do you do to find, what's IT equal to? What did y'all learn? IT would be equal to V of the source, add them up, divided by RT, right? So I'd say IT would be equal to 10 volts divided by 6K. So what does that give me? I know y'all got a Windows calculator. What's that? 1.67 watt. $1.67. We gotta have something else out there. 1.67. It's got to be ohms. It's got to be amps, or it's got to be volts. What's this going to be? What are we solving for?
Amps. This is 1.67 milliamps.
Yeah, milliamps. Good. Okay. So VR2 would be equal to 1.67 milli times 5K. What would that equal?
Was that 8.3?
Sounds right. So calculate the voltage drop across R4 for me. If it's 10K and 50K, so that's what going to be what? So VS is 10 volts over 60K. What's the current?
Oh, okay.
This is I, sorry. So this is IT. So what's this?
It's 166.67 micron.
Probably 166.7 micro. So VR4 is going to be equal to 166.7 micro times 50K. And if we round it, what do we come up and get? Hopefully it's 8.3 volts. Or close to it. Okay. So V4 equals 8.3. Yeah, it's the same, but notice the ratio. This is 5 times greater than that. This is 5 times greater than that. So as long as the ratio is exactly the same, then they're going to drop the same voltage as the other side. Does that make sense?
Yeah.
Okay, so let's come over here and say R2. Let's say VR2 would be equal to R2, which is 5K divided by RT, which is 6K. I'm going to get rid of the K right off the bat because they're on the top and the bottom. And then I'm going to multiply that by 10, and what do you come up and get? 5 divided by 6 times... Okay. This is what we call the voltage divider formula. Now, which would you rather do? Would you rather do all this math right here to calculate 8.3, or would you rather use the voltage divider formula? The voltage divider formula says the voltage drop of a resistor is proportional to the ratio of the resistors to the applied voltage. So what's the ratio over here? Well, over here I'd say VR2 is equal to what? 10K. I'm sorry, wrong one. We're trying to find the bottom resistor, Rich. Would be equal to 50K divided by 60K. Wow. K is going to mark out. Zeros on the top and the bottom, 5/6 of the voltage. I multiply that by 10 and I get what? 8.3 volts.
8.3.
But here, you're solving for voltage without solving for current, right? You understand that? Okay. All right. So we call this thing balanced. To be balanced, the ratio of the resistors on the left has to equal to the ratio of the resistors on the right. Okay. So voltage divider formula. So let's say my sensor, I'm using a photo resistor over here. And I want a certain amount of light to equal to 0 volts. So let's say I have this set for, I know we're running out of time, guys. Let's say I have this set for 2K. And over here, this right here, I'm going to leave that 10K up there. But this thing right here is giving me 5K. So my voltage drop over here, VR2, would be equal to what? 1K over 3K. And what's going to cancel? Times 10. What's going to cancel? K will cancel. Okay. So what voltage will we have setting right here? R1 plus R2. Yeah, so the formula is voltage divider formula is VRX is equal to V is equal to RX over RT times VS. That's the voltage divider formula. Can y'all see that one?
Okay.
So we did what?
That's RX.
RX. This is the resistor you want to solve for. So right now, I'm solving for R2, right?
No, R1 because you got the 1K.
No, I'm solving. This is where our measurements is relative to this because this is our circuit common.
Yeah, but you just put 1K right there and then the space by the VR2.
Okay, thank you. I understand now. I was just seeing if y'all was paying attention. So this is 2K divided by what? 3K, thank you. times 10. So the K is going to cancel out, so it's going to drop 2/3 of the voltage. Now VR4 would be 6.6. Good. Okay, so R4 is going to be 5K over 15K. I'm getting ahead of myself. No, it ain't. See, the ratio's different. Over here, this is 2 times bigger. Over here, this is half of it, right? So this is going to be...
Yeah, that one is 33.3.
Oh, no, I'm not there yet. Over 15K, right? K is going to cancel. So this is going to drop, what, 3/5 of the voltage.
33.3.
Can't be 33.3 because all we're working with is 10 volts, right? So sometimes y'all should realize your answer. So the most I could drop would be what? 10. And So what did y'all got? 3.3 volts? So over here I got 3.3 volts. Over here I got 6.6 volts. So what's my meter going to measure?
3.3.
Good. And it all depends on... Yeah, it's going to measure the difference. So what we can do is I can put a sensor that changes its resistance like a photoresistor. And then what I can do is I can set a 0 value. So let's say I want the light in my room here to be my reference. Well, what I can do is I can turn this pot right here to this meter measure 0. And then from then on, the measurement will mean something. Y'all understand what I'm saying? So what a Wheatstone bridge gives us the ability to do is to set a 0. So like if I had a temperature sensor, like if I wanted, if this was a temperature sensor, well, that temperature sensor is going to give me a resistance and it's going to drop a voltage even when I've got the thing, when I'm measuring 0 degrees centigrade, right? So, or Celsius. So what I could do is I could take my temperature sensor and I could put it into a glass of ice water and then I could adjust this until it measures what? Until it measures 0. So what we do is we use a Wheatstone bridge on devices where we need on sensors that change their resistance, and I need to set a 0 reference. So if I balance this thing right here, if I set the ratio of these two resistors to this over here, my meter's going to measure what? It's going to measure 0 volts. Now if my temperature goes up, then this voltage right here is going to change, and now the change in voltage is going to mean something, right? Does that make sense? So we'll run into this. You'll run into this a lot on resistors, on a sensor that changes its resistance with what it measures, and you need to set a 0 reference. So like a scale. Anybody had any dealings with scales? So those sensors are actually resistors, and we need to set a 0. So a scale you got to set a 0 on, right? So that's what a Wheatstone bridge is. A Wheatstone bridge allows us to do what? It allows us to establish a 0 reference. So all we would do is we'd hook up our sensor. We'd have a pot that's big enough. And then what we would do is we'd put our reference. What do we wanted our reference in? So if it was a liquid level sensor, I'd say, okay, I want to put 0 water in there. Well, that liquid level sensor is going to give me an R no matter if there's water in there or not. The R might go up and the R might go down with water, but I need to set a 0 out. Well, what I would do is I would turn my reference pot right here until my meter measures what? Until it measures 0. And now it means something. Now, if it measures 5 volts, that means there's water in there, and then I could do a transfer function, and I can say 5 volts equals to 100 gallons. So I don't know. The problem is y'all are supposed to be getting Wheatstone bridges back in DC. I need to make sure this happens because you're going to run into these in sensors. And this is going to be a sensing element that changes its resistance. Now, currently, we've only talked about one, and that's the photoresistor. But even if you put that thing I turned all the lights off out here, and I looked at my ohm meter, it would measure an R. But I want that R, if I turn off all my lights, I want that R to mean my lights are off. So what I could do is I could put it in a Wheatstone bridge. I could turn all my lights off. It would be hard to do. And then I would adjust it till my meter measured 0. And then when I turn my lights back on, the intensity of the light would be relative to some base. So that's what it allows us to do. So right now, the only sensor that we would use this in would be for a photoresistor. So that's the only sensor we looked at that varies its resistance with light. Okay? So good. If y'all got any questions, just either if you send me a text, if you put me a message, send me a text that says, hey, check your mail or whatever, and I'll go in and I'll answer that for you. Okay? All right, guys. Thanks for everybody showing up. It's really good. I was talking to some of my other instructors, and they're having problems with their students showing up. I really appreciate that. We got 16 people in the class, and we had 16 people show up. I really appreciate that. Thank you. They're gonna think I've been judging on my.
More people to show up when we're not in there.
Yeah, I know, but there's nothing I can do about that. It'll show up on the test. So, y'all have see y'all Wednesday. We'll have our test at the end. So we're gonna look at speed sensors. So y'all might want to look at the PowerPoints on that. We don't have any labs on speed sensors, but I got a bunch I can show you. Okay.